Hello and welcome to today's webinar, Developing a Deep Rock Grouting Design from Start to Finish. My name is Jessica Williams and I'm the Marketing Manager at Avanti, and I'll be playing host and moderator for this event. Before we get started, I did want to let all of you know that there is a question function in the GoToWebinar panel. If at any time during the next 60 minutes, 75 minutes, you have any questions that come up, definitely put that in the box and we will answer them at the end. Now I'll let our speakers introduce themselves and then we'll get started. Brad?
Thanks, Jessica. I appreciate the opportunity to continue this webinar series. Thank you all for the opportunity to do that. I'm Brad Crenshaw. I'm the General Manager of Ground Engineering Contractors. We're a contracting company out of Knoxville, Tennessee. And we'll introduce Adam, who's going next. We're adding additional credentials and intelligence to these things, so more so than Britt and I have. So Adam, go ahead.
I appreciate it, Brad. My name's Adam Bedell. I've been tunneling for probably about 20 years now on the design side. I've been dealing with deep grouting for about 15 of those years. Worked in the design, the construction. I've been underground during the process, and and I really appreciate the opportunity to help join in this webinar.
All right, thank you, Adam. Thank you, Brad. My name is Britt Babcock. I'm the president at Avanti International, and I've been around construction of all different types for a little over 25 years now, and really look forward to this presentation and the value and the knowledge and the mind share we're about to get from Brad and Adam. Many decades of experience there that we're going to get to enjoy.
Great, thank y'all. Before we jump into the real content, I want to throw out a poll question for y'all. It should be launched on your screen. Question: what role do you play in the development of a grouting design program? Owner, contractor, designer, consultant, other? Take a few seconds and we'll share the results. All right, just a few more seconds. Votes are coming in. All right, now as you can see, it's pretty even spread. Designer, consultant, 35%, 38%, so 3% owner. All right, Britt, take it away.
All right, thank you, Jessica. Great spread there on who's involved in this presentation and who's attending. So thank you everybody for attending. As we've said at the beginning, today's focus is on deep rock grouting, the design process. What we're going to focus on, Jessica, there we go. Took me a second to advance. We're talking about grouting, and the first thing we need to define, or we should define, is what really is the purpose of grouting. What's the goal of grouting? A lot of times when we're thinking about grouting, it gets looked at from a lot of different perspectives, but maybe it's in and around a tunnel, or it's in and around a shaft, or it's on a smaller scale, they're buildings, or they're walk-through tunnels, things like that. But the purpose of grouting really can be boiled down to two primary goals, and that's to stabilize the soil and rock that may be in and around those different subterranean structures, or to also control groundwater. It really can be boiled down to those two primary goals. From a structural perspective, we may be wanting to increase the strength of a rock mass or a soil situation. Obviously, we're talking about deep rock grouting here, so I'll reference rock in that situation. Or controlling inflow, again, groundwater, right? So we boil back down to structural support of a rock or controlling groundwater. We're looking at potentially the volume, how many gallons of water do we have coming in, or the velocity. Velocity definitely plays a role as well when you're considering how to grout or how to attack those different solutions or challenges. So there's two primary grout types used in geotechnical applications. One way more so than the others, but we'll talk about that here in just a minute. There's cement grouts, also known as particulate grouts, And within the cement grout family, there's ordinary Portland cement, which, believe it or not, we believe, and I think it's generally believed across the industry, is predominantly used 95% of the time in geotechnical applications when you're in rock fracture grouting. Sometimes the geology will tighten, and within that same family, you'd use an ultrafine cement. Ordinary Portland cement has a typical micron range from 75 to 100 microns on average. But ultrafine cements, and I'm grouping in microfine, ultrafine, superfine all into one. Those are three grouts within that ultrafine family, if you will, typically hover around 3 microns on average size. Microfines are 8 microns. Superfines can be as low as 1.5 micron, but predominantly that only gets used about 4% of the time in the geotechnical applications. And the other half of the grouts, the other type of family within the grouts is the chemical grouts, also known as solution grouts. Those consider the resins or the polyurethane grouts, and then also known as solution or chemically reactive grouts. Those only get used about 1% of the time. So pretty interesting that we're looking at, ordinary Portland cement. I think everybody on this call would also attest to that. That 95% of the time is ordinary Portland cement gets used for deep rock grouting situations or any geotechnical application. 4% is ultrafine, and 1% really is the chemical grouts. Kind of a quick snapshot in penetration grouting, like rock fractures or things like that, where Portland cement might be used to fill a void, might be used to be an excavation support or mining support, injection into fractures, rock support or rock consolidation situation. Believe it or not, the ultrafines can do the same thing in a lot of situations. You wouldn't necessarily use ultrafine in void fill because it's just not cost effective, but ultrafine gets used in a lot of the same situations as Portland: rock support, compensation or fraction injection and excavation support. But then you may use ultrafine cement for compensation grouting as well, where it may be needed. And then, even though it's a rock feature and it's grouted like a soil, I threw it in here, matrix porosities, where ultrafine cement might get used as well. So just an interesting couple of slides just to kind of show. But what's our outline of the presentation today that Adam and Brad are going to share with us? We're going to start with the delivery method, right? How are we going to take care of that grouting project, specifications versus contracts? And then what type of information are we going to need from Mother Earth? What type of soils data information? And Adam's going to go through a good detailed explanation on that. Then we're going to dive into the details of an overall design, concept to delivery. And then we're going to go through project mock-up for a shaft as well as a tunnel TBM. And then we're going to end that with some real world experience that both Adam and Brad have had, and real world applications. We're going to share that with you. So one of the questions that may be in the back of your mind is, why deep rock grouting? How is that different than shallow rock grouting? Well, there's a lot of things that come into play. These are the key top 5. Your feedback and grouting data in your excavation is going to be different. Your pressures are going to be higher, much higher than that of a shallow. Your equipment for delivery is going to be different, mobile versus modular. It's definitely a much harsher environment at depth, and your entire cost structure may be different as well. So one of the reasons why we've singled out deep rock grouting versus that of shallow rock grouting in this presentation. So without further ado, I will now pass this on to Adam and let him run with it. Thank you, Adam.
Thank you, Brett, for the background information. So I wanted to take a quick moment and just kind of walk through some of the larger details. One of the first things we need to do is I want to really kind of frame how this presentation is set up. When we're talking about grouting, we're really kind of looking at it from a pre-excavation perspective or a post-excavation perspective. And when it comes to grouting, you can kind of go down either one. There's a lot of, hybrid cases when it comes to grouting. And so this particular presentation is framed from a pre-excavation grouting perspective. With pre-excavation grouting, we're really trying to get out and deal with the situation ahead of the excavation. With post-excavation grouting, we're really kind of dealing with the water after the fact. And so while a lot of the same principles apply, we're either dealing with the water after a cast in place concrete liner has been in place, or maybe the tunnel boring machine has already passed through a very wet section. We'll still have to deal with the water at some point. But also when you're talking about post-excavation grouting, you know, the implications for a tunnel are different than a shaft. I mean, with a tunnel, are we mining upgrade to where the groundwater that we encounter flows out of our excavation, or are we mining downhill such that we now have to pump it out? Similarly for a shaft, you know, we have got to, if we're dealing with the water later, we still have to get that water out of the shaft. And so again, we're kind of looking at this from a pre-excavation grouting perspective. We're trying to get out ahead of the problem before we hit it. So with that, you know, we do need to touch a little bit on specifications and contracts. You know, when we're talking about grouting programs, a lot of times we use what are called prescriptive specifications. And that's where the engineer comes up with basically the entire grout design. You know, we're coming up with the grout mixes, we're coming up with the whole layout, we're coming up with the methodology, the refusal criteria. We're basically laying out the entire design. Now, part of this is that the risk of the program working really kind of rests with the engineer. You know, typically for specifications like this, we're typically using unit rates to pay for them. So on the design side, we establish bid items. We provide the contractor with estimated quantities, how much drilling, how often is that grout pump going to be running, how much cement can you expect to use, and then the contractor will provide us their unit rates. Another way grouting is typically handled is through performance specifications. And this is basically where the engineer will lay out, you know, basically a performance criteria for what is the requirement after grouting has occurred. And so the designer will say, you know, the shaft can only make 30 gallons a minute afterwards, 20 gallons a minute, some number, and then it's up to the contractor to design the grouting program to come up with the means and methods, the grout mixes, the whole array, everything to meet that performance specification. Now, one thing that you need to keep in mind is that, you know, we need to make sure that the performance requirement or the criteria is reasonable, and we'll kind of get into that a little bit later. Typically, these types of contracts are paid for on a lump sum basis. And so this is where, as the contractor owns all of the means and methods and the risk associated with the program working, a lump sum grouting bid is submitted. And now another way that grouting programs are handled, I mean, sometimes if there's emergency work that occurs, you know, if you're mining along and you have a groundwater inflow that occurs into your tunnel or shaft and the general contractor can't deal with them, well, then a grouting contractor will come in and address the issue. Typically, these are paid for on a time and material basis. Now, even though I've broken these up into these three different categories, it doesn't mean that you can't have different payment types for different types of specifications. I mean, you can have prescriptive specifications that are paid for on a time and material basis, but generally these are how everything is broken down. So as we get into kind of the design details of how to design a grouting program, you know, the thing is that, you know, both the engineers and the contractors are relying on this geotechnical information to design. You know, the engineers are using it to either design their structures, their shafts, their tunnels, their dam foundations, while the grouting contractors are looking at it from a, you know, how are we going to do our grouting program? You know, the bottom line, as we all know, is that the less that we know about the ground, the higher the costs. Typically, you know, for these investigations, either a geotechnical data report, a data report, geotechnical data summary report, these are what's used to present the factual data about the ground. This is strictly the test results, the laboratory results, the boring logs, stereo plots, things of that nature. But the bottom line is that there is no interpretation associated with these reports. But the thing is that as we're collecting all this information and you're in the beginning phases of design for your project, you know, you need to be thinking about grouting, you know, and whether or not it's going to be used, it should be considered. Because really, if you're designing a shaft, a tunnel, a dam foundation, you know, any of these things, a lot of the same information that you're getting that we need to design these structures, they can be used for on a grouting basis. And so one of the first things that we look at, you know, triple tube rock coring. We use them in dam foundations, tunnels, shafts. We use them a lot. It's almost like the backbone. What's the rock? What are the discontinuities? What's foliation? What's bedding? We look at RQD, we look at recovery, we look at photographs. I mean, and the thing is, though, is that this is giving us direct information about the rock mass from the core sample. Are the fractures lined with clay? Are there any sort of linings to where grout penetration can be lessened because of the linings along those fractures? But, another thing that we look at is hydraulic conductivity testing. And this tells us a lot about the rock mass. And we use them all the time, but it's amazing how often we don't use them. And these are used for all sorts of applications: dam, foundation design, tunnels, shafts, mining. We use this everywhere. And it's not just the permeability of the rock mass or the permeability of the discontinuities if you're looking at it from, say, a crystalline bedrock point of view, but really from a grouting perspective, it gives us direct information on how groutable is that rock formation. And the thing is that we're typically using Packer tests to determine this information. We're also using pump tests. Do we have a primary or a secondary permeability? And it's really, I can't stress it enough how crucial it is to the grouting process. But it's also one of the most important tests that we run, because as you can see from the photographs, it gives us the most, it mimics the grouting process closer than anything else. We're injecting a fluid under pressure back into the rock mass. And the thing is that if we're not going to be able to inject any water, it's going to be very difficult to inject any sort of grout. Another tool that we use often is borehole geophysics. And what's nice about borehole geophysics is that it really allows us to fine-tune our grouting program. If early stages in the design process, we have set aside vertical boreholes or grout holes around our structure, and then we look at the borehole geophysical data, we're able to fine-tune, because if the fractures are at high angles or based on their orientation, we have a high likelihood of missing them with our grout holes. We're able to fine-tune. Maybe we spin our holes around the shaft. What are areas that have a very large fracture aperture? We might want to target those zones a little bit differently. But the bottom line is that we really need to know the ground. We really need to know what's out there. And again, it's almost that you're designing your grouting program in concert with the design of your overall structure, because you're using all of the same materials.
Great, thanks, Adam. So we'll jump into quick poll question number 2, and it should be launched on your screen. The question: what project type or types have you designed a rock grouting project for? Shafts, tunnels, mines, deep foundations, multiple of the above, or none of the above? Give it about 10 more seconds. All right, let's close it out. Share the results. 64% say multiple of the above or none of the above. Let's just hope that most of those are multiple. We ran out of space for questions there, so we threw them both in. All right. Adam, back to you.
Thanks, Jessica. So we know about the ground. We know all of the methodologies in which we're gathering information about the ground. We know what kind of things that we're looking for. And so when we start laying out the design of the grouting program, what we're really looking for is, the first thing, it's really kind of like the macro level view, but, what's the purpose of the structure? Is this a subway tunnel? Is this something that to where it needs to be dry, or is the shaft going to primarily be filled with water? Because a lot of these things are built below the water table. It's kind of, okay, well, what do we have? What exactly are we building? The next step is that we really need to look at the intent of the grouting program. While a lot of similarities exist between, say, a tunnel, a shaft, or a dam foundation, there's a lot of nuances between each program, and, principles associated with dam foundation grouting, while there there may be some similarities, or there are some similarities between that and tunnels, but they're different. You're working under different conditions. And so, really kind of, are we just trying to limit groundwater infiltration, into the shaft? Are we trying to make things manageable during construction? What are we doing? And then after we think we know what we're doing, let's really take a better look at what we're doing, because a lot of times, people will look at grouting. It's like, oh, well, we're going to seal off all the water. Well, sometimes grouting is going to work and sometimes it's not. I mean, this kind of ties back to um, the realistic expectations for, say, a performance grouting spec. If something has to be, if I'm looking for a shaft that makes 3 gallons a minute, am I really looking at grouting to accomplish that? Can grouting accomplish that? And a lot of times, because this is tied into the specs, I mean, just given this example, we have to have a watertight shaft. Well, how reasonable is that? Is it to expect that, below the water table, and to where you won't have any leaks, drips, or seeps? It's really not that. It's really not that practical. And if something truly does have to be watertight, why don't we use a membrane? But I would like to point out that, I meant to say this back in the perspective section, a lot of this reflects North American grouting practices and not necessarily other parts of the world. A lot of the grouting criteria, say in Norwegian, it is a lot different. And whilst there's some similarities that exist, grouting pressures, grout material, and things like that nature are different. And so I forgot to mention that earlier. And with that, I'd like to turn this over to Brad, who's going to talk about shaft grouting.
Thanks, Adam. I think that that background is great information, especially the information on the geology, because it's a good introduction to what I'm about to talk about. So I'm going to sort of talk about the information associated with the shaft pre-excavation grouting design. So I threw this slide up here, and the intent of this slide is not to read it and go through everything, but this was just sort of a brainstorm on my part, to kind of look at maybe some of the things that we may consider whenever we are trying to design a grouting program. And I'll be honest with you, there may be some stuff that overlaps in here and everything like that, but it just goes, the point of this slide is to go to show there's a lot of stuff to consider, right? That being said, a lot of that information is going to come into focus once we can decide on a grouting method. And 100% the grouting method has to be based off of the geology. So everything that Adam talked about, all the geologic testing, all the information that needs to be gathered, that goes into determining your grouting method. And once you determine a grouting method, you then can start, there's a lot of rules of thumb, there's conventions, there's empirical information, there's all this stuff that can be used to develop a proper grouting program. So you determine the grouting method, and then after that, there's not that much typically that really has to be figured out to do a good grouting program. So as you can see on this slide, you determine your grouting method. This leads into the other slide a little bit. We'll discuss that a little bit more, but we're going to make an assumption on that based off of this presentation of deep rock grouting. And after that, then you've got some stuff to figure out about your grout holes, the number, location, orientation, and depth, and the grouting type. Amount is probably not so important for a technically successful job, but having a reasonable estimate is certainly important for a financially and contractually successful job. So we will cover that a little bit just because it comes into play, and a lot of people have a question about that. So the grouting method. As I alluded to, this presentation is based off of deep excavation grouting of rock. Based off of deep excavation and grouting of rock, almost all of that, probably 98% of those projects are going to be what we would typically term consolidation grouting. When you do consolidation grouting, then you are grouting the brittle deformation features of a rock mass. So that's going to be the fractures and the lineaments and the faults and those sorts of things, the things that formed essentially after the rock itself formed. And when you do that, then I think that although there's a lot of dissent in the grouting community about certain things, you will always go to a flow and pressure refusal criteria. I put up sort of a typical example on this. The other thing that the other, I guess, option here would be matrix primary permeability grouting. I'm going to refer you back to one of our previous webinars. If you want more information on that, we won't discuss it here. I did think that it was worth throwing out. This is sort of along the lines of what Adam discussed, that what I have presented here with the pressures especially are based off of U.S. convention. In other parts of the world, then typically you may go to a higher grouting pressure, which in my professional opinion, I don't think is bad. I think that there's some value in that. However, we work within the conventions that we work within, so it's important to understand those conventions. Again, the pressure flow criteria, refusal criteria is the important aspect of consolidation grouting. There's other methods. One of those is known as the GEN method, and you may hear about that. However, at least in my opinion, it really does not have a place in deep grout curtains for rock. So go back to the thing, grout holes. So you've got all the geologic data gathered. It's been given to you as much as you can get, and you have decided that you are doing consolidation grouting, which again is brittle rock features, filling those up. So automatically that gives us sort of a rule of thumb, a convention, where ultimately our final hole spacing is going to be somewhere between 7.5 and 10 feet. Typically for a shaft, as you can see over here to the right, you will do sort of a perimeter around that shaft. Two reasons, rather than sort of a staggered pattern within the shaft and around the shaft, is that the circular pattern is more economical. You use less holes. You just fill the area around the shaft, which you're concerned with. But also, if it's, say, a raised bore shaft, you have less chance of losing drill steel within the actual excavation, which could be a problem for the excavation equipment if you were to do that. So hole spacing of 7.5 to 10 feet. So essentially, if you calculate the circumference, divide it by those, you have a rough idea of the number of holes. So where do you space those outside the shaft? That's a pretty typical question. And typically the best answer to that is you space it outside the shaft, just sort of to limit the amount of grouted material that you will be excavating, because it does you no good to pay for material that will be excavated. So for sort of a less destructive method, such as a raised bore or a blind bore or something like that, you can be, say, 1 to 5 foot outside the shaft, because there'll be no real sort of overbreak. Typically for a drill and blast, you're a little bit further, 5 to 10 foot, because you're going to be something outside of the neat line, and you account for that. And, I'll bring this up again, go back to our previous webinar. This is not so much based off of grout travel. This is just based off of don't pay to grout what you're going to blast out. Another thing to consider is that the holes could be angled. Adam mentioned some information about this based off of the geology. Typically, an angled hole is going to be done to address high angle fractures. The important thing to understand on this is that what's going to control whether you can or cannot do this is the geometry of the shaft. So going to this slide, here's an example of a shaft that was designed with angled holes. If you have a high probability of high angle fractures, then this is a great way to approach that. But here's what you've got to realize, that whenever you lay those holes out, as you can see here, you start, well, let me describe this. This inner circle is the excavation of the shaft, if you can see those that I'm tracing there. So you start a little bit further outside the shaft. As you drill these holes, you will come to some minimum distance from the neat excavation line of the shaft. And as you extend past that point, you get further and further away from the shaft. So if you see this outside circle that I'm tracing here, eventually you get too far away from the shaft so that now your holes are no longer at that 7.5 to 10 foot spacing. So essentially, once a shaft gets too deep, which depending on the exact geology is typically somewhere between 200 to 300 feet, but it depends on the overburden also. It becomes very hard to do this from the surface. It's a possibility from underground, but just a consideration. Overburden, shaft depth play into your ability to angle the holes and address the fractures through this means. So back to grout holes. We're still looking at we've got the number, the orientation, those things. Now we're back to we're looking at how deep to take those holes. And Adam did a great job of going over the importance of hydraulic conductivity testing. It is for consolidation grouting. It's the number one piece of information that I think is important for that type of work. So we need to look at that data. Over here on the right, this is not designed something for you to read, but that's simply the raw data for hydraulic conductivity testing was given in the geotechnical data report. And the raw data is really important so that the grouting contractor can make their own interpretation of that information, because they may have a empirical way of looking at that data that they need that raw data for. So you got raw data over here. Here's the raw data summarized. And then here's a calculation of hydraulic conductivities for multiple step tests here. And then a average Lujan value. And again, the understanding Lujan values is important in the previous webinars it's gone over. But here's some rule of thumbs. There's a general correspondence between Lujan values and hydraulic conductivities. Those are kind of listed out here to the side. But typically for consolidation grouting conditions, if you have a hydraulic conductivity of 10 to the negative 3 centimeters per second, no problem. You grout that all day long, great results. 10 to the negative 4, depending on the exact characteristics, you can have good results, average results. You may want to start looking at, say, a microfine in that situation. 10 to the negative 5, you're probably not going to do much with Portland cement. You might can do something with a microfine, ultrafine, or if it's important, it may not be important to grout it. Back to Adam's point, if it is important, then you probably need to be looking something other than typical. But you only need to extend your grout curtain to these depths. If you don't have data, or if you have a situation where you need to grout the entire shaft length, then typically you're going to go somewhere between, say, 1/2 to 1 shaft diameter below the shaft bottom to get far enough down to cut off any water that may be coming up from the bottom of the shaft, or if you have a shallower or a known confining layer, then you may be looking at that layer. So that kind of runs through just the thoughts on the grout holes. We get into the grout, which is the next probably important thing to consider here. Grout type, again, we had an entire webinar on this, so refer back to it if you need more information. But the number one indicator in my experience of what's going to be successful when it comes to grout type is the previous experience on that site, or some local knowledge of the geology. So it comes down to the geology. However, that being said, typically for consolidation grouting, you're going to use a cementitious grout. Britt alluded to the fact that 95% of that's going to be Portland and 4% is going to be microfine, ultrafine, superfine, which I think is probably very reasonable. Type 1, you may be able to use if you need a minimum amount of water cut off. Type 3 is very standard and typical and generally creates a degree of cutoff that's acceptable for safe working conditions and typical geologic conditions. Microfine or ultrafine, if you're looking at that, then you probably need a higher degree of cutoff than typical, or you have some kind of unique geology. And if you're looking at a chemical, then you're probably looking at some kind of unique geology. And then grout amount, obviously, that's the $100,000 question on most of these jobs. Again, if you have some kind of previous experience in that geology, that is the best predictor of what it's going to take to do it the next time. If you do enough grouting, then it's important to save your data. There can be empirical calculations that are developed that have a decent degree of I guess accuracy would be the right word for that. However, I'm going to throw this out there, and this is sort of one of those things that you just learn over time. Probably 18 years of just grouting, a bunch of grouting projects. All grouting projects that I've ever been involved with that were designed properly have resulted in a grout take of between 20 to 190 pounds per linear foot of drilling once they were complete, with an average grout take of about 75 pounds, which sounds like a big range, probably. Really not. That's basically between 0.2 and 2 bags per foot. So when you're looking at this and trying to put a budget together, it just gives you something to go by. Now I understand that you may not know exactly how much drilling there's going to be when you start, because that's something you evaluate as you go along. That being said, if you go through the stuff that we've gone through, you can come up with a reasonable estimate of it if you know enough about the geology. That being said, I will turn it back over to Adam.
Brad, I appreciate it. You know, as you were going to the last slide, I just started thinking about it. How many times have we actually gotten the cement take correct over 15 years? You know, it's like
did once.
once. And so that was a lot of great information. So I'm going to kind of walk through, as the slide indicates, I guess, a kind of a project mock-up. And so I'm going to look at something from a TBM perspective, but then also something from a drill and blast perspective. And so again, I can't stress this enough, and I'd mentioned this previously. You know, again, why are we grouting? What kind of information do we have? Do we need to probe? You know, we kind of talked about specifications a little bit. Do we have enough information for prescriptive specs? You know, or if we're going performance, are those the goals of those realistic? So here's a project that we worked on. It's in Blandtown, USA. And so we have a couple of borings, you know, kind of scattered around. And so, you know, RWB 20 right here we measure, water level, you're measuring it at just under 270 feet. We've got RWB 22, and we measured the groundwater level at about 30 feet below ground surface. We're in the same geologic unit. At this point, just imagine you're early in design. We know that a tunnel is going to come between these two. So just looking at the water levels, I mean, we're not even getting into the other stuff, but just looking at the water levels, you're like, something's going on through here. I'm not sure what. I don't know what kind of machine they're going to have. I know it's going to be TBM driven, but I mean, again, this is just imagine you're in the early stages of design. There's still a lot you don't know. So you kind of look at this, and so, again, what's the first thing we do? What's the intent? What are we trying to grout here? We know we have to do something. Well, we know that we've got a very steep gradient, and really we're looking at, we're trying to reduce the amount of groundwater infiltration, into the tunnel. We want to maintain a safe excavation. We want to keep things manageable, during the mining. So what do we know? Okay, well, we're going to probe. We know that. Well, if you're going to probe, what's your grouting trigger? Okay, well, we've got an idea on, what that's going to be. Are we going to grout? I don't know if we're going to grout. It all depends on what we find with the probe holes. What do we not know? Well, we don't know specifically between, borings what's going on. We have an idea. I mean, we're in the same unit. We know that something's going on there. We don't know what kind of TBM is going to be procured. We know that we've got a tunnel going through there. And we don't know what the grouting capabilities of the machine are. I mean, even if it is not uncommon to either, if you pick up a Heron connector, if you pick up a Robbins, and your drills are supposed to be able to rotate X number of degrees, so we can put rock bolts in at exactly 11:30 and 1:30. Oh, we can't put them in until 2 o'clock and 11 o'clock. Is that okay? We just can't get over the main beam. So, I mean, it's a big consideration. So how do we deal with this? Well, we say, Mr. Contractor, we need you to retain the services of a grouting consultant, and they're going to submit a design for a grouting program. Now, what we've done is that we're going to set aside an allowance item to cover the cost of the grouting, but also the TBM sitting there, because, the TBM excavation is just about always on critical path of the project. And so you need to account for that cost when you're setting aside your allowance item. One of the big things with grouting specs is that you've got to be clear in what the intent of the program is and what you're trying to do. If you're not clear, well, then the contractor isn't going to be clear, and there's going to be question, and you're going to get answers or an increased cost. But then what you can do is provide prescriptive specifications, and because you've already gone through design, you've got all the grouting information, all the grouting data, that the grouting contractor needs to allow them to adequately design and submit the grouting program once all of the unknowns are now known. And so, for this example, it's like, here's a submitted probe zone overlapping, how are we going to probe? We know what the triggers are. If we have groundwater inflow through this probe zone, this is the sequence that we're going to grout the machine. If we have groundwater infiltration and grouting is triggered from there, this is how we're going to alter the grout injection sequence. So now we're going to kind of turn over to a drill and blast operation. So we've got a river over here to the left. We have a creek tributary kind of coming through the screen, and we know that we're drilling and blasting a tunnel across this creek. And so we know the location of the tunnel. We know that it's a drill and blast operation. And so, but what we don't know is, how bad is the rock underneath the creek? So again, we start with the design intent. What are we trying to do? We're just trying to reduce the potential for that direct hydraulic connection to the creek. Again, maintain a safe and stable excavation. And we're just trying to keep groundwater inflows to a manageable level during the course of the construction. Well, for this particular case, we actually know, we know a decent bit. We know where we want to probe. We again know the grouting triggers. We know that grouting may be required. Now we know the excavation style, and it's like, okay, well, we know the excavation style, we know how we're doing it. Well, I've got grout hole arrays, lengths, distances, grout mixes, all that stuff. What do we not know? We don't know what the actual potential is for that hydraulic connection. Maybe it's super high. Maybe they're going to have to install ribs and lagging down at tunnel depth. We're not sure. So what did we do? We basically, from an engineering perspective, we designed the entire grouting program and we provided prescriptive specifications. We were able to establish the bid items, and we came up with estimated quantities. How much drilling are you going to do? How often is your grout pump going to be running? What is your cement take going to be? And so one of the things, so when you're probing, and this is just a personal pet peeve. When you're probing, I don't like the idea of just probing out in front of the heading in a horizontal line, because really now you're paying for drilling twice. If you're going to probe out ahead of your excavation, you might as well make the hole worthwhile. And so, if you know how you're ultimately going to grout it, then choose a probe hole that fits in with that scheme, and so you can make that beneficial. And so this is what we did, and we provided a plan and profile to where the contractor knows that grouting and probing ahead is going to be on in a fan style arrangement.
Great, thanks, Adam. So we will jump into our third and final poll question. And that is, at what phase of projects do you typically consider the use of grouting? Conceptual, project design, construction phase, unforeseen emergencies, or all of the above? All right, give it a few more seconds. All right, so let's close it out, share the results. And as you can see, about 60% say all of the above.
That's a good answer.
I thought so too. All right, and we'll go back down.
Thank you, Jessica. Okay, so we've gone through a couple of mock setups. We've gone through shafts. We've gone through drill and blast tunnels. We've gone through TBM tunnels. And the purpose of the mocks were to try to kind of point out some high level stuff and make stuff to where it was it would really kind of jump out. Unfortunately, when we start interpreting grouting data related to projects, it's not necessarily the case. And so this is a project to where we were looking at the potential for grouting shafts. And really, if you're looking at it from a design standpoint, it's really not that dissimilar than when you're looking at it from a design of the actual shaft or structure standpoint. We've got geotechnical data that has to be organized in a meaningful manner. We need to make determinations of what's too far off in alignment, or the distance to your profile. But then we have to start building it. And so the borings that are represented in these columns, they extend down to the bottom of the page for each one. And you start kind of looking at it, and you're looking for zones within the core that are, where did we lose core? Where did we have core that had clay and weathering, say by these orange sections? We've got a high degree of weathering along the core in those areas. And then how do those correlate with, say, where did we lose core? I mean, maybe we drilled these holes and we had a geologist out on site, or maybe a third party drilled and logged these holes. You just have the boring information, you've got nothing else. And so you're kind of looking for everything. Did you lose the drill core because it washed out? Did it fall out of the core barrel? Could you not find it? Did it not make sense where it went? All you know is that you don't have core here. Okay. Well then, where do I have permeability? So you plot up all of your permeability data and take a look at that. And the thing is that as Brad had mentioned, once you start getting into a hydraulic conductivity of 10 to the -5 or 10 to the -6, I mean, you're really not going to grout it. And so when you plot up all of the takers that are below that, and you start looking at it, and everything down here is 10 to the negative 6 or greater, all of my grout takes are up higher. And then you note that they don't necessarily coincide with areas of poor, weathered rock or areas of lost core. And this is where you're building the picture to where even though the core looks like this, or even though um, you've got a sandy material, or maybe you've got clean fractures at depth, in a crystalline environment, and you don't have clay line fractures. If you're not injecting water into it, you're not going to get grout into it. And so what this tells me is that in this particular area, I'm not going to really inject any grout. But in this area up here, I can do some grout. Okay, and so, but this is only half the step, because really the next step is the cost benefit analysis that you always have to do. Are these two structures going to make 30 or 50 gallons a minute? Say that they're and also, are those small diameter, or are they large diameter? If it's a relatively low inflow, because after you come up with how you're going to do it, or what you can do, you still have to go in and design it. And if you estimate a price tag of $2 to $3 million for your grouting program for 50 gallons a minute, that doesn't make sense. It's not practical. Your contractor is just going to slap up some panning and just, let it run down the shaft walls. It's more of a nuisance water at that point. But if you're looking at, oh goodness, this could be, 1, 2, 300 gallons a minute within the zone. Oh, well, now it makes sense that we can provide some value. We can provide some benefit here. And so it's not just a culmination or a combination of all the data, provided from the boring logs. You've got to look at it from a cost perspective also, to see if it's really worthwhile. And so with that, I'm going to turn this over to Brad.
Thanks, Adam. Based off of everything that you've talked about today, that's one of those jobs that we like as contractors. Whenever you give it to us as a performance spec and give us all that data and say we got to get it down to less than 100 gallons per minute, I'd bid on that. But it just goes to show how important it is to have the data, because a lot of times, just being honest, sometimes you just have to decide there's no reason to grout. And there's a little bit of that in this example that I'm going to talk about also. So mine's going to be a shaft also. And I put back up sort of the same slide as I had thrown up before, talking about these most common parameters, because again, these are the things that are probably going to be most important. Other things start becoming important typically if for some reason there's something that's different. But for this, it's not. It's pretty typical project. So the method, again, because we're talking about deep rock grout curtains, then we're assuming that it's brittle deformation, consolidation grouting, so we're filling fractures. That's our assumption that we go into this design with. And in this case, the reason that we do that is because this is actually for a mine, and they actually they provided us a borehole which confirmed typical geology for the type of ground that we're in. We had experience doing shafts in this type of ground, not exactly in this area, but with this type of ground. And in this case, the mine owner did a very good job of going in and hydraulically characterizing the ground so that we had something to go off of. So that's the background. That's what's important in this. And really why we were able to go in and sort of maximize or minimize the grouting process per se to sort of maximize the program for the owner. So this was going to be a drill and blast shaft. Based off of that, going back to the things that we were looking at, that means that we're going to put the holes about 5 foot outside the neat excavation line of the shaft. Again, a lot of people think this is, they have this picture in their mind. They think this is because you don't want the rock bolts to punch through, or you don't want all this. That's not the case. Go back to the rock grouting webinar. Cementitious grout travels a tremendous distance when it's pumped under the right circumstances. Limiting the distance is our problem, not how far we can get it. This is simply because we want to minimize the grout that we're excavating. For this case, the shaft radius is 11 feet. So if you set the grout holes 5 foot outside, that's a 16-foot radius grout curtain. Simple math. You run the circumference calculation, it's a little bit over 100 feet. So divide that by 7.5 feet, as we had talked about before with our assumptions, because we're consolidation grouting. You get about 14 holes. Divide it by 10 feet, you get about 10 holes. So now we need to be somewhere in that range for our initial considerations. And I always, you don't have to, I always like to go with a number that's divisible by 4, because I like to use a primary, secondary, tertiary grout sequence. So I'm going to go in and I'm going to drill and grout 3 primary holes. Then I'm going to split space those, go halfway between, and do 3 secondary. And then I'm going to go back in and go between all of those. And the reason I like to do it that way is simply because I have a lot of data from previous experiences that tells me how the ground should behave when the grouting is done that way. Split spacing is very typical. People may do it at a little bit different distances. These are the distances I like. I also like to, as far as budgeting goes, I like to leave an allowance for quaternary holes. So I may need to go back in and drill some extra holes between these, just based off of the data that I get back, the feedback I get from the primary, secondary, and tertiary holes, because the ground is telling me what I need to do. In this case, we decided the holes would be vertical, simply because, to be honest, it's a sedimentary type formation. So most of the fractures are fairly horizontal. There's not a indication of a large number of near vertical holes. So there's no need to go to the trouble to do a complicated design there. Here was the really important information for this shaft. As you can see over here, this is the reduced data. The owner also provided the raw data, but they actually went in, they did hydraulic testing, packer tests, but they went to the extra step and they actually calculated what the estimated inflow would be for the excavated shaft for each 10-foot interval. So you can see these numbers over here. Let's do this one. 34 feet below ground surface for their borehole, test borehole, to 44 feet. They, based off of hydraulic testing, would have an inflow into the shaft of 1.21 gallons per minute. Not a lot, probably not enough to worry about. But as you start getting down to some of these others, there's some large ones. Now, the shaft was actually about 300 foot deep total. However, this table just summarized the important information. Below 134 feet, you started getting down into those 10 to the negative 6, 10 to the negative 7s, where the inflow was going to be so minimal, it didn't matter. But based off of all that, we decided that we did not need to grout 300 foot to the bottom shaft. We only needed to grout far enough below this zone where water could be produced to get a seal. So we decided we would grout down to 150 foot. Important thing here, I really didn't talk about it before. Stage length, hugely important when it comes to consolidation grouting. I could probably do a whole presentation or a third of a webinar on why. But typically, 10 foot is probably the best stage length. It gives you the best, most economical grouting cycle that you can get. However, long holes, sometimes we go up to 20 foot. Typically, we will not want to exceed 40 foot for a hole done from the surface. Now, if you're looking at probe holes like what Adam was talking about, we may go longer simply because of the economics. But for a surface pre-etch grouting program on a shaft, 40 foot is probably the max. 20 foot is reasonable. 10 foot, you maybe want to be a little bit shallower, but your stage length is hugely important. We're going to use type 3 cement. There's two reasons. Because it's conventional. Number one, we've already talked about that. But number two, we do have some local experience in this geology. We did a shaft down the road like 10 years ago, so it went well. So we have some idea that'll work. So I just wanted to sort of throw this up here and put some actual data in here so that you can kind of see what the estimated quantities look like versus what was actually done. So here you can see these were our estimates that we gave the owner. We figured that we would need 2,300 linear feet of drilling. That was the 12 grout holes to 150 feet plus contingency amount, which was probably 20% for extra holes, quaternary holes, if needed. The stages are simply the 2,300 linear feet divided by that 20 foot that I gave you, and cement bags. So essentially, we had the water test data, we had the raw data, so we were able to go in and take the raw data and manipulate it to come up with our version of a reasonable estimate of what should be injected. And then I threw out the actuals here just so you could see how they sort of compare. The drilling, we underran a little bit. I'll discuss later. The underrun was primarily because we did not need the quaternary holes. The stages were about right, so we obviously had some shorter stages that we're not really figured on. And the cement bags, they went over. They went over about 43%, which a lot of times that may sound like a lot, but realistically, for grouting, that's not a huge difference. I feel like it's one of the better estimates. But that being said, it also falls within that range, that reasonable range. And it probably, I don't know exactly, but it probably works out to somewhere around that 75 pounds per linear foot that we discussed earlier as sort of a typical for a well-designed program. So what were the differences? Once we actually got into this job, our data, the water test data, indicated that below about 134 feet, there would be no take. We chose to go a little bit lower than that, just sort of so we could get a cutoff zone, but also just because geology is variable. Once we got down there and we started doing the work, we actually had some pretty high takes between 130 and 150 feet. So we decided to increase the number of the holes to 180 feet, just to make sure that we got as deep as we needed to go. Obviously, as we went over, there were some higher grout takes than we estimated, but we felt like that was within reason. And we did have one of the reasons that we do the primary, secondary, tertiaries is so that we can compare the reduction in grout takes. And so we did have this one anomalous stage on the technically the last tertiary hole between 110 and 130 feet, we had been seeing grout takes of about 2.5 bags per stage. So that's on tertiary holes, just tertiaries. We've been seeing a grout take of about, so that's about 250 pounds per 20 feet. So, 25 pounds per foot, something like that. But then we had this one stage where we pumped 17 bags into it. So that's concerned to some. Based off of those concerns, we talked with the owner and we said, okay, we could put 2 quaternary holes on either side of this hole and check that out. That was one of the discussions. The other idea was that we could go in and we could put some probe holes down once we got to the, say, 100 or the 90 or 100 foot level and just see what we got. It was obviously much cheaper to put those probe holes in, and based off of the results, the owner felt good about those results. So that's what we decided to do. Save the money. Don't do it from the surface. Do it from underground. Turns out that the general contractor put those probe holes down, and one of those holes did hit about 8 gallons per minute. And may not sound like a lot, but in a shaft, then it becomes harder to deal with water because it's always on top of you. So the contractor was very concerned about that 8 gallons per minute. Called us up. We told them, here's what we suggest. They said, can you help us? And so we said, yeah. We sent a guy up there all the time, from lowering the hoses down to hooking up to grouting it to being done, took about 3 hours. Other than that, there was obviously minimal water inflow. There always is. As Adam mentioned, grouting does not get you dry. Grouting gets you minimal water inflow that you can handle with reasonable means. And then essentially below that 100 and somewhere between 150 to 180 foot, there was little to no water inflow, which essentially just confirmed the water test data. But the important aspect of that is not that there was no water there, but that the owner probably saved about half the cost of this project simply because they had taken that test data that probably cost them $2,000 or $3,000 and probably saved them $150,000 in grouting to prove that grouting that would have just proved what their $3,000 worth of test data told them. So ultimately, that's a pretty good result for the owner in that. In summary, then I'll just go over this. We've kind of hit this, but there's a couple of things that are worth mentioning probably here. Number one is, what's the goal? And this is a summary of the total slides. Water inflow structural. Not only that is, what's the goal for the structure itself? What's the goal of the grouting? What do you want to achieve with the grouting? The injection type that comes down to is really comes down to the type of ground. So you got to understand the geology. The geology dictates the grouting. Is the most important thing. If you don't understand the geology, you'll never get the grouting right. Once you understand the geology, you can understand your injection type, whether that's going to be consolidation grouting or permeation grouting. Again, previous webinars we've done, other types we haven't talked about yet. And then you can get into the specifics, grout characteristics. So you've got, your different grout types that'll be chosen, how long it needs to last. There's cost implications, and your familiarity with the grouting system itself. So there's a lot of things that come into it. There, just like the slide I showed before, there's a million different parameters, but get the geology right, get the grout type right, and then you can start making reasonable decisions. And I think that's is that right? Nope. I'd do it 2 slides, Jessica, but I'm done. That's all I can say.
All right. Fantastic. Thank you, Adam. And thank you, Brad. What a great presentation. What a great 75 minutes we've spent together here. We've got a Q&A time now. We've got several great questions that come in that have come in throughout the last hour and 10 minutes or so. One of the first ones that really pops out to me is what depth is considered deep? I think that's probably and you guys may have mentioned that on the call during your presentation, but Brad or Adam, is there sort of a threshold that when it transfers from shallow to deep, or is it a fine line, or is it a transition of grade between the two?
I think for me, it's a personal opinion, and it sort of just comes down to the certain situation, but I'm going to say about 50 feet and below, obviously.
I would say once you transition into fresh rock and you're sufficiently down to where you're below any sort of weathered horizons. And so, I mean, it's also going to depend on where you're at, as far as from a geologic standpoint, what's your current terrain, how thick's your overburden. And so it's basically making sure that you're sufficiently in fresh rock. I mean, if you've got 100 feet of overburden, because you're in some sort of sedimentary basin, then you're probably, to be considered deep, you're looking at 150 to 200, and greater.
Okay, fantastic. All right, we've got about 4 or 5 minutes left, so I think we can answer 2 more questions. For a large diameter shaft greater than 20 feet, would you propose additional grout holes in the center of the shaft, only grouting below the bottom of the shaft? For a large diameter shaft, would you propose additional, or greater than 20 feet in diameter, would you propose additional grout holes in the center of the shaft to deliver grout below the bottom of the shaft? I think is what they're inferring there in that question.
This is almost like creating a plug.
Yeah, and I can. Yeah. Here's the thing, and this is going to go right back to it. It depends on the geology. A couple of things throw out there real quick. Number one, your grout is going 20 feet. You've got holes out at, your grout curtain diameter, say, is 30, 40 feet. Grout travels that far easy, right? No problem. So it's not a matter of grout travel. However, if you have higher angle joints that you may think go across the shaft, you may want to consider it. But again, it comes down to your geology. Obviously, you have to have, if you're talking about a situation where you could have some sort of other transfer method besides a lineament or a fracture, so you're talking about like primary permeability, that's totally different. But for consolidation grouting, what we covered in this, typically not necessary unless there's some specific geologic reason why you should do that. We've done hundreds of them without it, no problem.
Fantastic. Great question. We've got several other great questions on here, but we are out of time in order for us just to have time to wrap things up. I want to thank everybody for attending this webinar, and I want to give Brad and Adam both a moment to say some closing thoughts. Brad, would you go first, and then Adam, how about you go second, and we'll close it out?
Sure. All right.
Closing comments?
Yeah, no, I just, first I'd like to, Jessica, Britt, thanks for the opportunity. Jessica, again, I think you did a wonderful job putting this together. We appreciate the opportunity to do this. I know that, Jessica, you have information on the previous webinars that we've done, which I referred to a lot. So if you don't mind sending that off to people, that'd be great. And look forward to doing this again. Hopefully we can keep doing it and people enjoy watching it.
Fantastic. Thank you. Mr. Adam. Thank you, Brad.
Well, guys, I just appreciate the opportunity. This has been, it's been fantastic. And Britt and Jessica, thanks for putting it together. And I really enjoyed the format to where it's kind of a yin and yang kind of perspective, a contracting side and a design side. There's a lot to consider. I hate the phrase grouting's an art, because I mean it's a material science, but it's also, there's a lot that goes into it, and so it's just know the ground that you're getting into.
All right. Thank you, Adam. This is Brett Babcock signing off. I want to thank everybody for participating. Some people may be wondering why Avanti's hosting a deep rock grouting excavation type scenario here, but the reality is we're trying to raise the tide of grouting, and it's all about doing what's best for the industry. And look forward to more of these. I think our next one we discussed is doing one on shallow rock grouting. So keep an eye out in your emails. We'll be pushing that out your direction here shortly. And I want to thank everybody for your time, your effort, and your attendance. Thank you.